Good. So then we can start.
Oh, both.
Excellent.
Hi.
Fantastic. Very good.
Hello, Roberto. Hello, Oscar.
Hello, how you doing?
Nice to see you.
Nice to
Good.
see you too.
Dear audience, I would like to welcome Roberto and Oscar Rodriguez Zaloña here. Our next speakers are online, and they're going to talk about user-assisted spectrum labeling with automated baud rate estimation. Please give them a warm applause. So, the stage is yours. Well, kind of, because we have pre-recorded your video, and we're going to play the pre-recorded video, as always with remote talks. And dear audience, you can raise your questions later afterwards. Our two speakers are going to respond to your questions. The same applies to the audience in the stream. Dear video team, please play the pre-recorded video now.
Welcome everybody. So I'm Roberto and he's Oscar, and we're going to present some joint work with Alberto Dassatti, and this is a user-assisted spectrum labeling system with automated baud rate estimation. And the idea is that given the spectrum allocation diagram, you're supposed to know emitting in a given band, at least for licensed bands, but those diagrams don't always tell you what is being transmitted and how. And that's why you need human experts to interpret what's in the air. Nowadays, we have machine learning systems which could automatically patrol the spectrum and recognize the emissions that are being transmitted. And the point we have here is that those systems require huge datasets for training, and while collecting data is cheap, in particular for radio frequency data, we just plug an antenna and we listen, and we can get as much data as we want. Having labeled data is very difficult, to the point that labeled data is the new gold. And this is because labeling data is labor-intensive, it's tedious, and it's error-prone. In this presentation, we present SpectroGrasp, which is an extensible open-source tool for spectrum exploration, which is aimed at easing the data labeling task, and which has some added bonuses. So it has an innovative automated baud rate estimator for symbol carrier modulations. It supports SIGMF and HDF5 formats, and it has an integrated energy detection system for both time and frequency, and native Onenex inference support. So, Oscar.
Hi. I'm going to present you the label tool that we have used in this project. You have to have in mind that this is a proof of concept, that it has extensive functionality, and it's also a work in progress. It's made in Python with libraries for visualization like Qt and pQtGraph. And as Roberto said, we support both SIGMF and GTLRF formats. The first one is a format provided by New Radio, and the other one is a format provided by MIT Haystack Observatory. Both are to store radio frequency data. So here you have an example on how can you open GTLRF data. You have to open a channel file. First, you will find the metadata of the channel in the graphical interface. You will also find some other places to initialize the model, let's say with some predefined labels and groups. And because this channel is empty, you won't find anything here. And also you have the annotation count and the label count that you can find in this file. Once you open it, you will find in the left some spectrogram parameters. In the middle, you will find the spectrogram itself, and on the right, you will find a list of the annotations. In the spectrogram, you will be able to adjust the levels, the colors according to the energy. So it's easier to detect the signals in the spectrum. I would like to say that this is a composed file, so this is not a real example, this is just a test, so we can visualize better how it works. We can also navigate through the spectrum, we can zoom in, we can zoom out, we can move to the left, to the right. We can adjust the different levels in the frequency and in time according to our needs. And once we are in and we can go back to the default setup of the spectrum. Once we work on, we can also export the image, so we can document it better, maybe for later. It's quite useful. And once we want to focus in some part of the spectrum, we can zoom in and we can manually select the part of the spectrum with the mouse. Just dragging, and once we want it to drop in, we can adjust the signal that we want to annotate, and we can see some of the metadata of the signal itself. We can also adjust it, or we can make it bigger, smaller. We can also see this is the annotation window, when you can see some details of the annotation itself. We can also have the periodogram of the annotated data in the spectrogram with some metadata of the annotation itself. You can adjust it to fit better in the periodogram in the frequency domain. You can add an author, you can add a comment. The symbol rate is something that we will speak about later. You can add a group, and you can add the label and also the confidence on the annotation itself. Once you add a label, it will be part of the model, and you can reuse it later for ease. So let's say that we just created an annotation with a label, my label, and a 75% of confidence. We can do the same several times manually. You can add another annotation. You can adjust it the same. You will see the list of annotations on the right. You can also adjust it better with the annotation window, sorry, and you can also complete it better with the label and again with the confidence. And you can also change the label in the annotation list on the right. And we can save it, of course. One of the things that Roberto commented is that we provide also an automatic labeler based on energy. And this is an example of how can you execute it. First, you will have to introduce the threshold in timing frequency, so it can adjust better for the signal that you can see in the spectrum. Yeah, and based on that, the automatic spectrum, based on energy, will create annotations. In this case, it has detected 17 annotations in the whole file, and you will have to go through all the annotations, and you will have to accept them, reject it, or just accept them all. Here we just put a default author and comments just to make it easy and to mark them as automatic detections. You will have to fill up the label manually, and you can also fill up the confidence as in the annotations that you created manually. And you also have the part that Roberto will speak later about the symbol rate estimation of the annotation. If you hit the calculate symbol rate button, it will launch the algorithm that Roberto will explain later, and then it will calculate the symbol rate if it is possible, because it's not always possible. Here we have some other examples. For example, for another automatic annotation, we have put the label and some confidence as well. We upset the annotation, and once we upset it, it's part of the model. In this case, for example, it seems that it's quite strange, so we reject the annotation, and in this case, we see that it's quite well fit. We put the label, we try to calculate the symbol rate estimation, but in this case, it's detected as a multi-carrier, so symbol rate cannot be estimated. Okay, we put the label, we put the confidence again, and we upset the annotation itself. For example, with an 80 or 75% of confidence. Another automatic annotation a little bit bigger than we wanted, so we adjust it. We calculate the symbol rate again, and in this case, the result is that this annotation has 300 symbols per second. We put the label, and so on and so on. For example, here we can see that the automatic method, it has detected the same annotation that we have manually annotated, so we rejected it. Here it seems that it's also kind of strange, so we adjust it, but we ended up rejecting it. Here, the same, we are already annotated manually, so we rejected it, and the same. And here, it seems that the process is working well, so I think we are gonna upset all the next annotations, so we don't have to go one after the other. So we just upset them all. Once we have a bunch of annotations in our file, we can do some annotations functionality, like we can merge them together. Like in this case, it seems that they belong to the same annotation or not. And we can also remove them, and yeah, we can do a bunch of different operations on annotations. And for example, here we have added another annotation that was missed by the automatic process, and we can save the model again. And here what we will do is we will close this window, and we will reopen the file again to see that the annotations are saved in the file, and we can work with them later. So we reopen the file, and here we can see that we have a different annotation count, different label count, and the labels that we have used during the annotation phase. And now we will show how can you run a deep learning inference with Onenex. This is related with the work that we presented 2 years ago. Here you will have to open an Onenex deep learning model or an Onenex model. Once you open it, you will have a bunch of metadata of the model, like the name, the inputs, and its size, and also you will have all the outputs provided by the model. In this case, the model outputs 10 different values. You can open a different file for the labels. And once you hit OK, it will run inference on all the annotations that you have annotated in the model automatically, and it will assign a label on each of the annotations. For example, here it's been labeled as default label 5, that one as default label 7, and so on and so on, with all the annotations in the file itself. So yeah, basically this is a tool to facilitate the annotations in huge data files, and with the automatic annotation model, annotation process, it's easy, and also with the Onenex inference, you can run deep learning inference in the annotated part of the spectrum. And I think it's quite easy. It eases the process.
So we get back to the presentation itself here. So to give you some more details on the automated Baud rate estimator, we can structure the system in several steps. The starting point is that you have a start and an end sample number along with the occupied frequency band, and this could be the output of the energy detector, for example, the one that is embedded in the SpectroGrasp system. And then what you do, you extract the signal of interest by doing some filtering and some decimation. As an example, here we have BPSK signal with a baud rate of 300 Hz, and which is normalized to 0.024 Hz. And what we do, we have it in the top picture. We center it, so we transfer it to baseband, and then we do the decimation, and you can see in the bottom plot that you have the decimated signal. And then we have to distinguish between single-carrier signals and multi-carrier signals, because this algorithm works only for single-carrier signals. What we do to discriminate between the two is to use the fourth-order cumulants, since multi-carrier signals are asymptotically Gaussian due to the central limit theorem. The point is that if by mistake noise somehow crept in and it was detected as a multi-carrier signal, we can, at this stage, remove it, because it has a different behavior if we look at the autocorrelation. So what we do is we remove the extreme values of the signals, and then we check the autocorrelation for spikes. And this tells us whether it's noise or multi-carrier. And the idea to get rid of extreme values is to deal with alpha stable noise, which would otherwise pose an issue here. Once we see that a signal is single carrier, we can continue with our analysis. And what we do is we nonlinearly transform the signal we did some initial experiments with the absolute value operator, but at the end, after some experiments, we settled to take in the arctangent of the signal, then we differentiate the result, and we compute the absolute value. If we look at the FFT of the transformed signal, we can then seek peaks in the magnitude plot of the positive half of the spectrum. So here we have the non-linearly transformed signal at the top from the arctangent. Then we differentiate it, and we take the FFT. The FFT, the magnitude plot of the FFT, if we look at it, we see there are several peaks. And if we exclude the central peak, the trivial one, we see that the first peak is exactly at 0.024, which was the normalized frequency at the beginning, the one that we had in our signal. The point is that, okay, we can see the peaks, but this has to be automated. So we have to make the system recognize those peaks. So what we do here is we sort the peaks by magnitude, and we keep only the n largest ones in the positive half of the spectrum. And let's say that we keep the first 100 peaks that we have in the 100 largest peaks. And we can see them, there are many of them on the left. Some of them are all together, but we also have one detected in the second highest peak. And then we check each of them. And we check them usually using the spectral coherence function, in particular using the frequency smoothing method. And this comes from the cyclostationary literature. And we do a trick. We remove the local median value of this function because this allows the true peaks to stand out. And we retain the cyclic frequency, which corresponds to the highest spectral coherence function value. And we consider a region around this peak. We also consider the first three subharmonics of the frequency we have found, and we take in for each subharmonic a region around it, and we take the maximum value in this region. Why we use regions? Because at the end we have quantized the FFT, so we have to take this into account, and we use regions to avoid to fall in the bin, which is just on the side of the real peak. Graphically, this is what we can see here is we have on the top the plot of the spectral coherence function, and on the bottom we have the same plot, but we remove the local median value, and we can clearly see that there's a peak at 0.024 corresponding to the our normalized frequency, and here we can just take the maximum in this graph, and it will output the frequency we were interested in, which corresponds to our symbol rate. There's still a problem because some modulation, like OQPSK, might hide the peak. So there's an additional processing step, which consider multiple shifts between the I and Q component, and we retain the peak that appears the most across the whole set of shifts we perform, and this allows us to detect the spectral, the symbol rate also for those modulation types. We did some tests on a proprietary dataset that contains 108 signals from a signal generator. So it was not a simulated dataset, and there were a bunch of modulations from ASK to QPSK, QAM, FSK, GFSK. And we artificially corrupted those signals with reflections, so using a ray light model and a Gaussian noise, having a 10 dB signal-to-noise ratio. And those are the results. On the clean dataset, we basically detected the whole the symbol rate for all the signals that we had, the same in the presence of reflections, and we still had a very good result when additional Gaussian noise was added. We are releasing a SpectroGrasp with an open license, and as Oscar said, it's at an advanced prototype stage, so all contributions are welcome. And we also want here to thank the sponsor that made this possible, Arma Swiss and the HOSSO. And this concludes our presentation. If you have any question, we will gladly respond to them.
All right. So Roberto and Oscar are here. First of all, yeah, thank you very much. Roberto and Oscar are right here with us, live responding to questions. So, are there any questions?
Hello. You showed your software at the, I think, pre-recorded IQ file. Could it also be used in a live environment, live decoding, and show what protocol or what baud rate is used on a signal?
I mean, the file that we showed, it was just a composed file. It was not a real file. But the formats that we support, they support any kind of recordings, I think. The both formats that we support, they are SIG-MF from New Radio, and the other was Digital RF from the MIT. And those kind of metadata can be embedded in the file itself. So as long as you follow the formats, the tool should be able to read it, and it doesn't matter, I think.
I think that for the live part, it's difficult because the computations that we do, especially for the detection, baud rate detection, are quite expensive, and I don't think it's ready for the moment to be executed live. But it's something that we would love to have, and that's also part of the reason that we release publicly, because maybe we will have someone contributing in that sense. There's nothing preventing it for operating live. It's just the fact of implementing it and having it sufficiently efficient in its computations to get those information live. It also depends on the bandwidth that you're exploring. If you have a 20 megahertz bandwidth, then I see it very difficult to operate. If you have 100 kilohertz, then maybe we have some hope of getting that.
Okay, thank you.
Any more questions from the audience? Marcus, did you had a look on the chat?
Torben? Any questions in chat? No questions.
Okay. Okay, so I think we are on time, and we have a little time to discuss more, or
okay,
we switch over to the next.
Well, then we have a little break for about 5 minutes, and we can take the time for some preparations. Okay.
Yeah.
Anyway, so thank you very much, guys. Roberto, Oscar, thanks for your contribution. Good that you're here with us today.
Thank you very much.
And hope you enjoy the rest of the conference through the live stream.
Mm-hmm.
Okay, excellent.